Okay, hi everybody. The point of this video is to run over trig solutions or trig equations and then how to solve them. And to start, I wanted to go over radians and what radians actually are. So radians are a way to measure angles just like degrees. Now in degrees, a full circle is 360 degrees. Half a circle is 180. Quarter of a circle is 90. And 3/4 of a circle is 270. Now, to be able to think about radians, well, all it is we take one full circle, or one full revolution, which in degrees is 360. For radians, we just say one full circle is 2 pi. It's the circumference of a circle with radius 1. So if you've got a circle that has a radius of 1, its circumference will be 2 pi. And so then we call going around a full circle 2 pi radians. Now, to get half a circle in radians, well, to go from, in degrees, to go from 360 to 180, we divide by 2. So to go radians full circle to half a circle, it would just be 2 pi divided by 2, which is pi. To go to quarter of a circle, well, degrees, 180 divided by 2 is 90. So then pi divided by 2 is just pi on 2 radians. Now 3/4 of a circle, well, if we take 90 and multiply it by 3, we get 270. So if I take pi on 2 and multiply it by 3, I'm going to get 3 pi on 2. And so then some of the common angles are 2 pi is a full circle in radians, pi radians is half a circle, pi on 2 radians is quarter of a circle, 3 pi on 2 is 3/4 of a circle. Now, that's okay for these particular values. But if we want the conversion to go from radians to degrees, well, we know that 180 degrees equals pi radians, which means if I divide both sides by pi, I get 180 degrees on pi is 1 radian. So if I'm going from radians to degrees, I want to multiply by 180 on pi. If I'm coming back the other way, I want to divide by 180 on pi, which is the same as multiplying by pi on 180. So either you divide by 180 on pi or you multiply by pi on 180. And so then the conversion is given by that particular chart there. So that's radians. Now, if we're thinking about trig, because that's the main point, trig always starts with the right-angled triangle. If I take a right-angled triangle like that, and I have an angle here, then the angle, or the side rather, opposite the right angle is called the hypotenuse. This side here is opposite this angle, so we call that the opposite side. This side here is next to the angle, so we call that the adjacent side. And so we get sine theta and these are your three big ratios. Sine theta is opposite over hypotenuse. Cos theta is adjacent over hypotenuse. And tan theta is opposite over adjacent. That's where trig starts. But then trig fairly quickly moves into use of what we call the unit circle. Now the unit circle is very simply a circle centered at the origin on the xy axis and has a radius of 1. So if I draw a circle, something like that, that's 1, that's 1, that's minus 1, and minus 1. Here my radius is 1 unit and it's centered on the circle. Now, if I draw a particular angle, and I'll do this in a different color, if I draw a line from the center to some point here, which we'll call P, then that forms an angle between the positive x-axis. Now, the positive x-axis very simply is here. It's where the x-axis is positive, unsurprisingly. So this angle represented by theta in here, well, that's between the line going from O to P, so we call our origin O, and the positive x-axis. Now I can draw a line straight down there and draw a line across, and that forms a right-angled triangle. Now because this circle has radius 1, the hypotenuse of this right-angled triangle is going to be 1, and this side here is going to be the x-coordinate of P, and this side here is going to be the y-coordinate of P. So P has coordinates x, y. So that's our x-coordinate of P, that's our y-coordinate of P. Okay, so let's just think about this for a minute and use our ratios that we've got up here. So in this right-angled triangle, I can say that sine theta is opposite over hypotenuse. Now, in this particular case, the side opposite theta is this side here, which is the y, whose length represents the y-coordinate of P. So it's y over the hypotenuse, which we agreed was 1, which is just y. Now, cos theta is the adjacent side over the hypotenuse, which the adjacent side represents the x-coordinate of P. Hypotenuse is still 1, so this is x. Now what that means is that the x-coordinate of P is cos theta, and the y-coordinate of P is sine theta. So sine theta and cos theta back here, where we agreed were opposite over hypotenuse, adjacent over hypotenuse, but we now have a new definition for them, which says that if we've got any point P on the unit circle, then the cosine of the angle between the positive x-axis and OP, this line here, well, the x-coordinate of P gives us the cosine, and the y-coordinate of P gives us the sine value. So, if I take a unit circle again, so draw up my x and y axes, Okay, so this is my unit circle. Now, if I draw an angle out here, that's P there. And for this angle in here, which let's say it's 45 degrees, which in radians is pi on 4, then the x-coordinate of this point is cos 45 and the y-coordinate is sine 45. So this is sine 45 cos 45, or, whoops, no it isn't, that is cos, the x-coordinate is cos, the y-coordinate is sine, or if you prefer, it's cos pi on 4 sine pi on 4 using radians. Now, I happen to know that the x and y coordinates of P, for this particular P, are 1 on root 2 in both cases. That's off the screen, so I'll move it down. So what that means is that cos 45 is 1 on root 2, and sine 45 is also 1 on root 2. Now, cos and sine of pi on 4 are also 1 on root 2, pi on 4 radians. Now, if I draw a line coming out here, let's say that this is at the same height there. And what that means is that this angle here is 135 degrees, or 3 pi on 4. Now from now on I'm actually going to be using radians in all cases because they're the ones we need. Now we can see that here the y-coordinate of this point here and this point here are exactly the same. The y-coordinates are both 1 on root 2. And the cos, or the x-coordinates, by symmetry are also the same. So this distance here and this distance here are the same, but the x-coordinate of this point will be negative because we've gone left. So if I was to give the coordinates of this point here, 1 on root 2, or negative 1 on root 2, 1 on root 2, and so we can say that cos of 3 pi on 4 is negative 1 on root 2, and sine of 3 pi on 4 is 1 on root 2. Now, if we were to take a third angle, let's say down here, and let's say the angle from pi to this is pi on 4, so we're still picking pi on 4 values, and so all up, the whole angle will be 5 pi on 4 radians. Now here, by symmetry, we can see that this point here and this point here are going to have the same x-coordinate, and it's going to be negative 1 on root 2. Now the y-coordinate, well, it's a fair assumption to say that this distance here and this distance here will be equal. So this one point down here will be negative 1 on root 2. We're coming down, so it's negative. So I can say then that cos of 5 pi on 4 is negative 1 on root 2, and then sine of 5 pi on 4 is negative 1 on root 2 as well. And then to go into the last quadrant, well, again, things would be very similar. The point, this angle, well, we're coming all the way around, we're going past pi there, then past 5 pi on 4 all the way around, and that gives us 7 pi on 4. Now obviously I've drawn it a little bit off because it doesn't line up very well with that point there, but its coordinates, well, it would have a positive x coordinate of 1 on root 2, and it would have a negative sine or a negative y coordinate of negative 1 on root 2, and so we could say that cos of 7 pi on 4 is equal to 1 on root 2, and sine 7 pi on 4 equals negative 1 on root 2. So these are just some exact values. These are some of the values we expect you to know and have on your unit circle. Now, the question also needs to be asked though, well, what happened to tan? We haven't introduced tan here, but tan is very simply, tan theta is sine theta divided by cos theta. And so then tan of pi on 4, we're dividing 1 on root 2 by 1 on root 2. So we're dividing the same thing by itself. So tan of pi on 4 equals 1. Now here, we're dividing 1 on root 2 by negative 1 on root 2. So tan of 3 pi on 4 is equal to minus 1. And you can go around and you could work out what it is for the other angles as well. Now, there are some what are called identities that are useful to know on the unit circle. Now, we can see here, now identities, first of all, I should explain, are just a relationship. So we can see here that if we've got an angle out here, and then over here we've got the same angle coming up there, then the cos values are negative and the sine values are the same. So what that means we can say is that, I'll actually bring this sheet in. So we can say that sine, so the sine values are the same, so sine of pi take theta is equal to sine theta, and cos of pi take theta is equal to negative cos theta. So here we had pi on 4. We said this was pi on 4 as well, so it's pi take pi on 4. Out here, that gives us the same sine values, and the cos value will be negative. So that's just one identity that we can pull from this diagram. Now, a more full unit circle is here. And I'll just have to move it. Oh, that should be alright. So this is a full unit circle. So you'll notice that the red are all, okay, well not everything's red, but y coordinates all the way around give us the other y coordinates, and so they're the sine of the angle. X coordinates are the cos of the angle, and then out in brackets I've given the tan of the angle as well. And you'll notice in here we've got all the angles, so that's 330 or 11 pi on 6. Here's 225 or 5 pi on 4. We saw that one before. Now you might say, well, why isn't that 1 on root 2 or negative 1 on root 2? The reason for that is negative 1 on root 2 and negative root 2 on 2 are exactly the same. Okay, so there's actually no difference. Okay, so we're going to be referring back to this in a lot of cases. All right. Now, if I had a trig equation, something like sine theta equals root 3 on 2. To solve this one, I would first go to my unit circle. And looking at my unit circle, I would be looking for y coordinates where I get positive root 3 on 2. Now, I've done a lot of practice at this, so I know where they are, so it's there. So my angle, one of the angles is pi on 3, but it's also there. So the other angle is 2 pi on 3. So I should say that theta equals pi on 3 and 2 pi on 3. Now if I just draw a unit circle again, we had pi on 3 being about there and 2 pi on 3 being about there, so that's pi on 3, and that there is 2 pi on 3. Now if I'm working on angles, the angle is always between the positive x-axis and the line from the origin to P, so it's there. So we know from there to there is pi on 3, all the way around there is 2 pi on 3, and that gives us sine of theta, sine of these angles being 3 pi on 2. But if I keep going past 2 pi on 3, come all the way around, I come to 2 pi, and then if I still keep going, I can come back to this line here. Now the angle is no longer pi on 3 because I've gone round an extra circle. So it's pi on 3 plus 1 full revolution extra, which is 2 pi. And if you add those, well, pi on 3 plus 2 pi is pi on 3 plus 6 pi on 3. So 7 pi on 3 also gives the same y coordinate, root 3 on 2. Because you see, by coming around here, another full revolution, the sine of that angle is still the y coordinate of this point here. And so 7 pi on, sine of 7 pi on 3 is root 3 on 2. So if I'm going to give the solutions for theta, 7 pi on 3 has to be included. But then I can also do a similar sort of thing for where it was 2 pi on 3. So starting at the positive x-axis, pi on 3 goes to 2 pi on 3. Then I come round and come all the way around to 2 pi. Then instead of stopping there, I keep going, go past 2 pi on 3 and go past go past pi on 3 to 2 pi on 3. For this angle, point P on the unit circle has a y coordinate of root 3 on 2, and so the sine of this angle is root 3 on 2 as well. Now in this case, it's just one revolution on from 2 pi on 3, so it's 2 pi on 3 plus 2 pi, which is 2 pi on 3 plus 6 pi on 3, so that's 8 pi on 3. So sine 8 pi on 3 is root 3 on 2 as well. So if I'm going to have all the solutions, 8 pi on 3 has to be included. But this starts to get very messy because you see, regardless of how many times you go around the circle, you see if I went around the circle another revolution, so starting at 8 pi and 3 here, then went round another 2 pi and came back to the same spot, I would still be getting a y coordinate of root 3 on 2, so sine of that angle would be root 3 on 2 as well. And so really, I can go around the circle, keep adding on another revolution, infinite number of times. And so that's actually means I've got an infinite number of solutions. And so we've got to think, well, how do we represent that? Now, we represent that by saying that theta is equal to pi on 3 and 2 pi on 3. We just give the solutions between 0 and 2 pi. And then we say, well, plus k 2 pi. Now, the k means that we can go around the circle or we can add on another revolution to either of these solutions an infinite number of times, and we'll still get the same sine value. So we can think of it as two separate solutions, so it's pi on 3 plus k 2 pi, and theta equals 2 pi on 3 plus k 2 pi. Both solutions are infinite, so we've got an infinite number of solutions here. Now k just represents how many times you're adding on 2 pi, so how many more revolutions you're doing. So k is a member of what we call the integers. So k is in the integers. Now integers are 1, 0, 1, 2, 3, 4. But they can also be minus 1, minus 2, minus 3, minus 4. But we haven't really discussed negative angles yet. So if I take a unit circle like this, from the positive x-axis to go this way is positive angles. From the positive x-axis to go that way is negative angles. Now, if I draw a line here, and we call that theta, down here, if that's also theta, this will be negative theta. If it's the same size angle, that it doesn't look the same, but we'll imagine that it is, then it will be negative theta. Now it's interesting to note that here both these points have the same x-coordinate, and by symmetry they'll have the same size y-coordinates, but negative theta will be negative. So we can actually say that sine of negative theta is just negative sine theta. The values will be the same, but because we're moving down for negative theta here, the y-coordinate will be negative. And then cos of negative theta, well, that's exactly the same. They're both positive x-coordinates, and so that will just equal cos theta. Now, the reason I just did that is that's another identity you might need to know, but also it means that if we go back a revolution from pi on 3, well, we've got to subtract 2 pi. And so we'll get a negative value, but that's okay. We can work with a negative value. So if I'm at 2 pi here, and instead of going forwards on, if I'm at pi on 3 rather, instead of going forwards on 2 pi, I could come back, go past 0, and then go into the negative values all the way around to here. And I would still have the same x and y coordinate for that angle, and so that's also another solution. So that angle would be pi on 3 take 2 pi, so I've gone back a revolution. So it's pi on 3 take 6 pi on 3. So it's negative 5 pi on 3. And so that's a solution to my equation as well. Instead of going on a revolution, I've gone back a revolution. It's a valid solution. So k being in the integers is a short way of representing those infinite solutions I have. Okay. Now, I'm sure you're aware that they do get a lot harder than this. And so probably the hardest they get is ones like this. Sine, or let's make it 2 sine x, let's make it 4x, take, I don't know, pi on 2, plus 1 equals 0. Now we start by boxing all of this together. This doesn't get split up. So initially, it's like, and it's not the same as, but it's like solving the equation 2x plus 1 equals 0. So what we're doing is we're calling this red thing x. Now, hopefully you know how to solve an equation like this. We take 1 from both sides to get 2x equals minus 1. Then we divide both sides by 2 to get x equals minus 1 on 2. So now that I've worked out, now x wasn't just an x, it was actually this sine 4x take pi on 2 thing. So to write that correctly, it's sine 4x rather, take pi on 2 equals minus a half. Now the first step in any trig equation is to do this. Get it down to sine of something equals a number. Then you go to your unit circle. So let's look for where sine, where the y coordinate is negative a half. Now we've got a y coordinate of a half there, but that's no good. We needed negative a half. So we come down here. Okay, I've got it there. So that's 7 pi on 6 and 11 pi on 6. So what that means is that this angle in here, this 4x take pi on 2, to make sine of it equal minus a half, well 4x take pi on 2 must be 7 pi on 6 and 11 pi on 6. It can be either of those, but it can be any solution added onto that. So we've got to add this k2 pi where k is in the integers. Now, this is where it tends to get a little trickier, but all standard algebraic rules apply. So 4x take pi on 2 equals 7 pi on 6 plus k2 pi. We've got to find x on its own. Now, if you think about, as I said before, all standard algebra rules apply. So to get x on its own, the first thing we've got to do is add 2 pi to both sides, or rather write pi on 2 to both sides. That cancels out there, so we get 4x equals 7 pi on 6 plus k2 pi plus pi on 2. Now I can't add k2 pi and pi on 2 because here they're not like terms. Here I've got this variable type thing of k. But I can add this 7 pi on 6 and pi on 2. They're just the same, they're just numbers, so I can add those. And if I add those, 7 pi on 6, pi on 2 is 3 pi on 6. So it's going to be 7 pi on 6 plus 3 pi on 6 plus k2 pi. So that's 10 pi on 6. So 4x will equal 10 pi on 6 plus k2 pi. Now, I also said that all standard algebra rules apply, so to be able to get x on its own, we've got to then go through and divide by 4. Divide both sides by 4. So let's just copy that equation. 4x equals 10 pi on 6 plus k2 pi. Now you might be trying to scream down the lines of communication that you can cancel that, and yes, we can. But I'm not going to bother at the moment. It's not essential. We'll fix it up later. So if I was to divide both sides by 4, I'd do that. And so x equals 10 pi on 6 plus k2 pi all over 4. Now, if I've got something all over 4, I can split the denominator. So I can say that's over 6 and that's over 4 plus k 2 pi on 4. Now if I've got that there, these two values will just multiply, so I'll get x equals 10 pi on 24. Now k 2 pi on 4, that cancels down to 1 and 2, so it's adding plus k pi on 2. Now 10 and 24, let's cancel that down, so dividing that by 2 gives us 5 and 12, so this solution gives us x plus 5 pi on 12 plus k pi on 2. Now that's fine, that's our solution, but let's say we want all these solutions between 0 and 2 pi. Well, 5 pi on 12 is between 0 and 2 pi, but before I go any further, remember to be able to add fractions, we need the same denominator. So if I go 5 pi on 12 plus k, and instead of writing it as pi on 2, I'm going to write it as 6 pi on 12. Same denominators, that's really good. And pi on 2 is equivalent to 6 pi on 12 rather. So then x equals, so the solutions are 5 pi on 12. That's the first one, that's k equals 0. Second one is when k equals 1. So it's 5 pi on 12 plus 6 pi on 12, so it's 11 pi on 12. Third solution is k equals 2. So 2 times 6 is 12 pi on 12, so 5 pi on 12 plus 12 pi on 12 gives me 17 pi on 12. K equals 3. Well, 5 pi on 12 plus 18 pi on 12, 6 times 3 is 18, gives me 23 pi on 12. Now, 2 pi is 24 pi on 12. So if I go to k equals 4, I'm going to be beyond 23 pi on, I'm going to be beyond 24 pi on 12. And so these are all your solutions. Now, that's only half the solutions though. We said that 4x take pi on 2 equals 11 pi on 6 plus k2 pi. But it would be exactly the same process. We would add pi on 2 to both sides, adding it to the 11 pi on 6. We would then divide both sides by 4, and then we would work it through. And so that would give us another set of solutions. I'm not going to show you how to do that. Now also be aware that if you get an equation with tan in it, it's exactly the same process. So if we had, I don't know, if we got it down to tan of 4 pi take pi on 2 equals 1 on root 3, we'd look for 1 on root 3 in the tan section. Okay, it's at pi on 6, and it's not there, but it is at, no, not there either. It's at 7 pi on 6. And so that would then, so 11 pi on 6 and 7 pi on 6 would go here. We would follow through the same working. So I hope you realize that in solving this equation, firstly you're getting it down to sine of something equals a number. Then you're applying the same algebra rules and then deciding which values of k you use to be able to get ones in your domain. Now, it's worth pointing out as well that if my domain was instead 0 to 2 pi, but it rather had been minus 2 pi to 2 pi, well, these would still apply, but we'd have to start we'd have to start using negative k values as well. So if k was minus 1, well, it would be 5 pi on 12 take 6 pi on 12, which is minus pi on 12. If it was, then it would be 5 if k equals minus 2. Well, 5 pi on 12 take 2 times 6 pi on 12, so take 12 pi on 2. So 5 pi on 12 take 12 pi on 12 is minus 7 pi on 12. If k is minus 3 times 6 is minus 18 pi on 12. So it'll be 5 pi take 18 pi on 12. And that, I reckon, is minus 13 pi on 12. Now if k is minus 4, well, 4 times 6 is 24. So it'll be 5 pi take 24 pi on 12. And that will give us minus 17 pi on 12. Now if k is minus 5, well, that will be minus 30 pi on 12. So 5 pi take 30 pi is minus 5 pi take 35 is minus 25 pi, and so that's beyond minus 24 pi on 12. So that one gets excluded. And so then that would be using negative values of k, that would give us more solutions. Okay, alright. Now it's been quite a lot to go through. Hopefully that clarifies things on solving trig equations. The last thing I do want to quickly run through is if you get it down to, so we were talking about getting it down to this stage, sine of 4x take pi on 2 equals negative pi on negative a half. Let's say you work it through to that stage and you get something like a quarter. Now, that, if you go to your unit circle, let's find where x coordinate is a quarter. So that's a half, root 2 on 2, root 3 on 2. That's an issue, you see. There is no y coordinate on this unit circle where it's equal to a quarter. So you can't use the unit circle here. You're not expected to do anything here because there are no exact values you can write for this equation. So this is where your calculator comes in. So if you go and you go to graph it, you graph your left-hand side, okay, sine of 4x take pi on 2. That's going to need to be in brackets. And then let's do 1 divided by 4, so a quarter on the right side. Let's draw it. Okay, so let's go view window, let's go 0 and to 2 pi. And then, okay, so draw it, gives us that little bit. Then we can do a zoom auto. So it fits it nicely. Now, we need the intersections. So if we're looking on 0 to 2 pi, we'd need to give them, so we can then say 4x take pi on 2, reading off the calculator is 0.456. It's going to be a lot of them. 1.11, 2.03, 2.69. It's getting a little tedious. 3.60. Notice I'm rounding to 3 significant figures. 4.26. 5.17. And then 5.83. Now, they're all the solutions for x between 0 and 2 pi. So in this case, I don't need to add my k2 pi. If I'm told that x is between 2 pi and 0, I just make sure that my view window goes between 0 and 2 pi, and then my screen will show me all the intersections for this domain. So there's no need to add the k2 pi as long as you're told the domain, but then you're going to have to go through and add pi on 2 to each of these answers and divide each of them by 4, which if I was to do one of those, so 4x take pi on 2 is just one solution, and that equals 0.456. So 4x will be 0.456 plus pi on 2. Okay. Oh, I've put in the wrong thing. 456. So that's actually by graphing sine of 4x take pi on 2, that's just given us our solutions there. So that is not necessary. So if we graph that, we get values there. Now, obviously, you're thinking graphing is a lot quicker. Yes, and you can graph as long as it doesn't ask for exact values. So that's actually the final thing we need to do for graphing. Ignore that bit there. And so then graphing to get the solution is a lot easier. And as long as it doesn't say exact values, you can graph both sides and then just write down the decimal values. Just remember to set your window to the domain, do a zoom auto, and you're fine. Okay, and that's the wrap on trig functions or trig equations and how to solve them. Hope that helps. Any questions, please ask me.